Hi, welcome back to Allen High School's discussion of electrochemistry at the AP/IB/HL level. Let's move on quickly here. Before I get into some more application of spontaneity, I want to summarize what we've discussed in terms of electrochemical cells. So we want to see what's alike and what's different. And it's best, right? The more you understand, the less you have to memorize. So our galvanic cell, that is the name of the spontaneous cells. They are often called galvanic or voltaic, so you need to be familiar with both of those terms. And in this situation, what we're doing is we're taking chemical energy and we're converting it into electrical energy. Our non-spontaneous cells are called electrolytic cells. Now, this is often, not always, but often how electroplating is done, plating of a metal onto a surface. And here we're going to use electrical energy in the form of a power supply or a battery, and we're going to use that energy to force a non-spontaneous chemical reaction to occur. All right, so that's different about the two of them. What is the same between both of these is the identification of the electrodes. Where reduction occurs at the cathode for both. Oxidation occurs at the anode for both, so that's the same. Now, this next one is especially important if you're in IB, and AP is ultimately not going to ask you this, but it is so important in terms of practical application that I'm going to make you learn this, whether it is an official quote-unquote AP objective or not. The sign of the cathode. If it's spontaneous, the sign of the cathode is after its namesake. So cations are positive, the cathode is positive, and that positive naturally attracts those electrons. The anode is named after its anions. Anions are negative. So the anode on a spontaneous cell is negative. So if you have a battery, the positive is the cathode and the negative is the anode. Now, it's opposite in a non-spontaneous cell. What we have to do in an electrolytic cell is connect these to a power supply or a battery. So we have to push electrons in. So it's the opposite. It goes against its namesake. Cathodes are negative for non-spontaneous and anodes are positive. So you do need to either be able to conceptualize that or memorize that. Now, the flow of electrons is the same for both because electrons are always leaving oxidation, half reaction, and they're always being received by the reduction. So that's the same for both of them. Electrons always flow from oxidation to reduction. This is true of the positive ions. Remember the salt bridge. Salts are ionic compounds, and the salt bridge is what allows ions to flow. And it's done to balance charge. This is a review. It's to balance charge. And if you don't have it, the cell will stop. A common misconception is that electrons flow. Can't write today. Electrons flow across the salt bridge. That's a common misconception you want to get out of your mind. Electrons flow up the wires. Okay? So, again, cations flow to the cathode. Again, you've got that namesake there, cations, cathode. And anions flow towards the anode. Okay? Now, again, the next one, what happens to the mass of the anode? That's the same. Because anodes, if the anode is part of the reaction, that means we have a metal. And we have a metal solid being oxidized to a metal ion plus some value A, right? Aqueous, so we're losing solid, so we see a decrease in mass. It's corroding. For the cathode, we're taking our metal ions in an aqueous solution. We're reducing them. We're plating out the metal ion. So it's a plating process. And we would see an increase in mass. So you see our key distinguishing characteristics here are our energy conversion, our spontaneity, and the conventions that are used for identifying the signs of the electrodes. So not too bad. So that's our summary for our electrochemical cells. We're going to do some examples and some really comprehensive examples. So until then, this is signing off.